Hello again, friends. Welcome to my home and to probably one of the more boring videos of this series, because this one's all about definitions and notation so that we can just talk better about the stuff we're talking about. So we'll start off with the partition. So we say that a partition, it always has to be on a given interval, and the interval always has to be closed. So if you remember, closed intervals include their endpoints. So we're always using square brackets to indicate. So we have a partition on an interval from A to B is a set of unique values. It's important that they're unique, where the first value that we're going to label x sub 0 is equal to A. The last value, which we have x sub n because the idea that there are n values, is equal to B. And for every value in the partition, it's going to be somewhere between A and B, right? A couple examples. This isn't that difficult a concept. It's just a new word that we have to get used to using because it's important. So on this closed interval from 2 to 5, we have a couple examples of partitions. So just the partition of 2 and 5. That's a valid partition. This one, 2.15. That's also a valid partition. 2, 3, 4, 5. That's a great partition. Ways that things could fail to be a partition. So this one with 2 and 3, this one fails because the last value in the partition is not equal to the highest value in the interval, so it doesn't reach all the way. This one, 2, 3, 3, 5, fails because the values aren't unique. We have a repetition, so this one is not a valid partition of the interval. This one, 1, 5, this overshoots on the less than side. 1 is less than 2, so it went too far. You've got 1, you've got 5, and our interval is from 2 to 5, so that doesn't really work out. And then similarly here, this one starts at 2 like it should, at 2, 4, and then 6, that's too big. So that's not a partition of the interval. Partitions are going to come up everywhere, but they're kind of a background thing. You just have to know about them. A valid partition always splits the interval into n subintervals. That's the reason why I started the numbering with 0, is so because say you had 3, if we went from x sub 0 to x sub 3, so we have our interval here. If we start with x sub 0, x sub 1, call this x sub 3, so then x sub 2, you'll see that, even though there are 4 values in the partition, they split it up into 1, 2, 3 subintervals. So that's why we started numbering with 0 here. For the ith subinterval, the length of the subinterval is going to be x sub I minus x sub I minus 1. And we use the symbol delta. This is the Greek letter delta. It's usually used to mean change or difference. Delta x with a little subscript I. So we've got our partition, 3, 4, 8, 21, 25. We lay these out on a number line, 3, 4, 8, 21, and 25. We can label these, if we want to use our x notation, our 3 is going to be x sub 0, this is going to be x sub 1, x sub 2, x sub 3, and x sub 4. We don't really need to label these almost ever, because what we're working with almost always isn't the actual partition values themselves, but the subintervals. So when we're looking at the lengths of the subintervals, our delta x1 is going to be x1, which is 4, minus x sub 0, which is 3. And that's just going to be equal to 1. Similarly, our delta x2 is going to be 8 minus 4, which is 4. Our delta x3 is going to be 21 minus 8, which is 13, and our delta x4 is going to be 4. So yeah, key value from here, just know about subintervals, but we are interested mostly in this notation for the length of a subinterval. Moving on. This is probably an unwelcome reminder from past classes, where you're going to be using a lot of what's called summation notation, which is using this, which is a capital Greek sigma. The reason that we use a sigma is because it starts with S, and sum starts with S. So no one here was creative when naming this stuff. So we're going to use a Greek letter sigma to represent the fact that we're going to be adding up a lot of things. If you remember yesterday, when we did left sums, right sums, and the trapezoidal rule, we were adding up a lot of things. So it makes sense that we should have some way to represent all these adding things. The notation is we have sigma from, you always start at the bottom, I equals m to n of x of I, means, so this expression here means to add together all the values x of I from I equals m to I equals n. So here's a couple of quick examples. We've got sigma from I equals 1 to 4 of 2. This is our sigma expression here. Well, this never changes no matter what I is. So for each I, we get a 2. So this is the 2 for I equals 1, 2, 3, and we stop at 4. We got 4 2's, add them together, you get 8. Here's a little bit more complicated. We've got sigma from I equals 0 to 5 of I. Well, this is going to change based on what I is. Since we start at 0, we've got 0 plus 1 plus 2 plus 3 plus 4 plus 5. Little bit of arithmetic gets us that equals 15. Just a quick example of using summation notation, where I probably won't end up actually adding this up. But say we had something even a little bit more complicated. Say we wanted to add up from I equals, I don't know, 3 to 8 of I squared plus 2, right? Well, each term in the sum is going to be whatever we are with I squared and then plus 2. So we'll start with 3 squared plus 2, that's for I equals 3, plus 4 squared plus 2, plus 5 squared plus 2, plus 6 squared plus 2, plus 7 squared plus 2, plus 8 squared plus 2. You know, I don't really want to add that up, but that's just to show you how you kind of get from a very compact expression, I won't say simple, to represent a pretty complicated sum. Everything that we're talking about here has a particular name, and it's called a Riemann sum. It's kind of hard to explain what this means. I'll show it better with an example here. A Riemann sum is any sum of the products of a function's value on a subinterval with the length of that subinterval over a partition, right? You could write this down. I highly doubt that you'd actually remember this. Generally written, a Riemann sum, which we use capital S for sub, with n terms in it, is the sum from I equals 1 to n of the function of some number, which might change over I or might not, times the length of the ith subinterval. So let's, for an example of how this works, define some things, right? So say our f of x is going to be x squared. Pretty easy peasy, right? Say our interval, Riemann sums are always over an interval. So our interval is from 1 to 5, always closed. And let's split this up on a nice partition, right? So for subintervals, we need a partition. So our partition is just going to be 1, 2, 3, 4, 5. We could have since we have 5 terms, a Riemann sum. Actually, this ends up being 2, 3, 4. 4 subintervals. So this is going to be a Riemann sum. Sum from I equals 1 to 4 of some, we're going to take, for CI, this is probably the most interesting thing. We can take it anywhere in the subinterval. So a fair Riemann sum would be at the midpoints, right? So it'd be, it's hard to actually use summation notations here. So an example of a Riemann sum here would be 0.5 squared times the length of the interval, which I made it equal to 1, always. So times 1 plus 1.5 squared times 1 plus, plus 3.5 squared times 1 plus 4.5 squared times 1. That's a valid Riemann sum. There's, even on this partition, you can have a number of different valid Riemann sums. So this is a perfectly valid Riemann sum. You could also do our left sum or our right sum from earlier, right? So a left sum would be 1 squared times 1 plus 2 squared times 1 plus 3 squared times 1 plus 4 squared times 1. That's a perfectly valid Riemann sum. The lesson I want you to learn from Riemann sums is that nearly everything we're talking about for the next 2 weeks at least, probably 3, starts as a Riemann sum. But you don't need to know, you just need to know that they exist. I don't need you to be particularly adept at defining what a Riemann sum is. You just have to know that what we're doing starts with Riemann sums. All right, so we're going to do some review with our new notation. So if we have some function f defined on the interval from a to b with a given partition, how would we write the left sum with summation notation? Well, we are summing from I equals 1 to n of our function f applied to the left-hand side of the subintervals, which is always going to be the smaller of the two, right? So if we wanted the subinterval corresponding with delta x1, we're going to plug into their function x sub 0. But since we have the I notation, we're going to have to change that to x sub I minus 1. So if we're on the first one, we need to get 1 less, so it'd be I sub 0. On the second one, we'll have I1, right? So this is f of x, I minus 1, times the corresponding length of the subinterval, so delta x sub I. And this is a great way of expressing a left sum. If we want to express the right sum, well, that's still a sum. It's still from I equals 1 to n, because we have n things. We still have our function, but instead of being applied to x I minus 1, we're just going to apply it to the right-hand side, which is xi. And it's still going to be times delta xi. Very, very similar. What does the trapezoidal look like? What does the trapezoidal rule look like? Well, it is once again a sum from I equals 1 to n. Every case we're summing up n things, except with the trapezoidal rule we had to average the left and the right bound, multiply them by the subinterval. So the average is going to be f x I minus 1 plus f xi divided by 2 and then times the length of the subinterval, delta xi. Very compact ways of expressing it, but in a way that you're probably not as familiar with just yet. You'll get used to it, though. Finally, we're going to prove an earlier fact that we hinted at earlier, and that's that the trapezoidal rule is the average of the left sum and the right sum. The way we'll get at that is, since this notation just stands for addition, it's just saying addition and multiplication, the laws of addition apply, namely the distributive law and the associative law. We can choose which spots to do at any particular time. I should probably also add in the commutative law. We can switch order at any time. These are all very helpful. So if we start off with the formula in summation notation for the trapezoidal rule, okay? So this is all like this divided by 2. That's the same every time. So rather than multiplying each term, which is as it's written out here, we can kind of factor out that dividing by 2. And now we get our summation. If we do that, we get our summation equals 1 to n of f of x plus 1 plus f of xi times delta xi. So our sum, and then we can, instead of dividing by 2 at each term, we can just do the summation divide by 2 at the end, which is great. Again, it's just addition. So we can take this and we can distribute this delta xi because it has to multiply anyway. So again, instead of adding first, multiplying, we can multiply through and we get 2 adds. So this would have to equal the sum from I equals 1 to n of f xi minus 1 times delta xi plus f of xi times delta xi all over 2. Well, that's also great. And this looks suspiciously like the left sum. This looks suspiciously like the right sum. They're just contained in the same summation. But again, this is just a lot of addition, but it's all just addition. So we don't have to do addition in the order it's written. We can indeed split this up. We don't have to do this addition inside each term. We can do all these additions and then all these additions. So this becomes one sum, I equals 1 to n, f of xi minus 1 times delta xi, plus the second sum, I equals 1n, f of xi, delta xi, divided all by 2, and that's what we wanted. This term, summation notation, is the left sum, or LRAM as they say in the book. This is the right sum, or RRAM as they say in the book. And this is just the average of the left and the right sum. So the fact that seemed to fit in all the examples we did yesterday is in fact true. And that's good to know. So rather than doing this every time, which I saw several students doing yesterday, it is oftentimes easier to just do the left sum, do the right sum when you have them, average the two. All right, that's enough for this one. Thanks for stopping by.